I almost can't believe that we are wrapping up yet another year on the podcast this month, which has been going strong for 6 years now. And it's been another exciting year in the world of Clin Micro as well, with improvements and new assays available for some of our bread and butter tests. But the year also brought about some significant developments in the application of AI and digital imaging, as well as use of NGS methods, and probably some cool AST stuff in there too, amongst other things. And many of these advancements have been published in the Journal of Clinical Microbiology. And so, as has become customary for the last 6 years, for this episode, we will be sharing some of our favorite papers or more intriguing manuscripts published in the journal this year. And I have to say, this is probably one of the hardest episodes for me to prep for, because picking just one paper to talk about is incredibly difficult, as you can imagine. But we are up to the challenge, and we'll share those with you over the next half hour or so, all while wearing ridiculous holiday sweaters and holiday headgear, as is now also our tradition. So if you're not watching, you may want to switch and find a video option for your viewing pleasure. Welcome to Editors in Conversation. I'm JCM editor Ellie Thiel, and I'm joined by my co-host, JCM editor-in-chief Romney Humphreys, who is looking particularly festive today.
Thank you.
What the heck are you wearing?
I am wearing my fellow's cubicle. I forgot that I was supposed to bring a Christmas t-shirt or sweater today, so I stole all of her decor. So thank you, Janice.
Well, you're definitely still looking festive.
I feel particularly festive. I feel like I should be in a parade or something.
Yeah.
You don't talk to me.
Well, we hope you've enjoyed previous editions of Editors in Conversation episodes, and ask that you please subscribe to this podcast and share with your friends and colleagues. This episode is brought to you by the Journal of Clinical Microbiology, available at asm.org/JCM. Editors in Conversation is supported by the American Society for Microbiology, which publishes JCM. And if you're a member of ASM, you can get up to 50% off of the publication fees when you publish in JCM or any other ASM journal. All right, so today we are happy to have not one, but two JCM editors with us to talk about a paper that caught their eye this year. So we are joined by Dr. Jen Dean-Bard, who is the Chief of Clinical Operations and Director of the Clinical Microbiology and Virology Labs at Children's Hospital in LA. Welcome, Jen. Happy to have you on.
Thank you. Excited to be here and excited to wear my one and only Christmas sweater.
Yes. So tell us about your Christmas sweater for those that are not viewing it.
I think I had to buy this about 5 years ago for a family party. And since then, it's been the only one that I wear and have. So I'm keeping the tradition.
Love it. Love it. We are also joined by Dr. Erin McElvania, who is the director of the Clinical Microbiology Lab at Endeavor Health in Evanston, Illinois. Erin, welcome to the podcast.
Thank you.
And is that a llama on your shirt?
It is.
A llama with glasses. He's a smart llama.
Yes, it is. It's a studious llama.
Studious llama.
And very much like Jen, not only are we llama matching, this is my only holiday sweater as well. And I actually had to steal it from my child. A few years ago, she needed one for school, and we went to multiple Targets to find it. Mm-hmm. And they only had adult sizes. So who would have thought years later this would really help me out?
It was a great investment.
Mm-hmm.
A great investment.
Mm-hmm. I just find it interesting. You each have one ugly holiday sweater, and you both have llamas on it.
It's the llamas.
So.
It spoke to me.
Yeah, I guess so. All right. Well, with that, I think we can dive right into our papers for today. Jen, do you want to start us off? What did you pick?
Sure. So this was definitely a difficult task because there were so many interesting papers as I was looking through the list in 2025 that was published in JCM. But the one that caught my eye was a paper that is entitled Inter-Laboratory Assays from the Fungal PCR Initiative and the Modi-Mucor Study Group to Improve qPCR Detection of Microalgae DNA in Serum. One more step towards standardization. The primary authors for this paper was Dr. Steffi Rocci from the University of Franche-Comté and Dr. Laurence Millon from Besançon University Hospital, both in France. Before I start summarizing this particular study in detail, I wanted to just give a quick background because the group has done quite a bit of work even prior to this paper. The goal of standardizing microalgae PCR is what they were focusing on. And the first inter-laboratory evaluation of microalgae qPCR assay was organized in 2017-2018 by the ISHAM working group. So this is the Fungal PCR Initiative, FPCRI. The majority of the group that was included in this study that I will be talking about was also part of the Modi-Mucor study group that previously published on evaluation of serum microalgae PCR for the diagnosis of mucormycosis. And this was entitled the Modi-Mucor prospective trial. So just very briefly, mucormycosis is a it causes severe invasive infections and caused by molds belonging to the order Mucorales. The diagnosis of mucormycosis is quite difficult as both clinical and radiographic findings can be non-specific and really tough to differentiate with other fungal infections such as invasive aspergillosis. So this Modi-Mucor prospective study was this multi-center study that sought to assess the performance of serum qPCR for the diagnosis of mucormycosis. And in this study, they reported pretty high sensitivity and specificity up in the mid to high 80s. And the authors argued that positive results from the microalgae PCR should be added to the mucormycosis diagnosis criteria in the consensus definition that's published by and this is going to be a mouthful, the European Organization for the Research and Treatment of Cancer / Mycosis Study Group Education and Research Consortium. And this is something that was already done for Aspergillus PCR in the most current version of the consensus definition. One of the arguments from the consortium to not include microalgae PCR criteria for probable mucormycosis was just the perceived lack of standardization. And the authors did acknowledge in their previous studies that of the 26 different protocols that they looked at, there were so many different combinations of DNA extractions, amplification techniques that it made it really difficult to determine which parameters would have the most optimal effect on the PCR test itself. So now, fast forward back to the paper that I wanted to focus on.
Hey, Jen, can I ask a question, though, before you jump into that? So we've been talking about this, I feel like since we did our fellowship, I think it was written on the wall as one of the tests that we should be thinking about insourcing. And I'm always worried about specificity, right? Because there's molds everywhere. Did they talk about that, with all of these different protocols that are out there?
Yes, they did, and that's one of the items that they did discuss a little bit, even in the study, because you're looking at. But I would say that the focus they had was sensitivity, and in the study they did find a couple of labs where there were contaminations and issues with specificity, but the main focus was sensitivity for this.
Okay, cool, thanks.
So to the paper. The aim of the paper was to perform an external quality control study to identify key parameters that can influence PCR performance. So this working group led the distribution of simulated samples to 26 different labs. So one panel consisted of serum that was spiked with microalgae DNA, and this is to assess the extraction protocol. And then a second panel, panel B, consisted of microalgae DNA extract, and the goal was to assess amplification protocol. So this topic spoke to me for two separate reasons. One, it highlighted just the lack of standardization across clinical labs with regards to protocols that are really considered standard of practice. Why do we do certain things? It's, some of it's because we were taught that way, but, sometimes there just isn't a lot of evidence to support it. And so it's typically up to the medical director's discretion, which, of course, can be beneficial, as some of these protocols can be tailored to meet the needs of your specific patient population. But at the same time, and especially with molecular tests, standardization can perhaps improve performance and provide consistency. And then the second reason, which is more selfish, was that, and what you just said, Romney, it has been on our list for forever, but we are currently working on developing our own fungal PCR test. So this really spoke to me as to, what can I do to improve the test that we're working on? So the study included 26 laboratories participating in the 2 trials. So as I mentioned, panel A was for DNA extraction and panel B was for the amplification portion. And the labs that participated included 12 laboratories from French university hospitals and then 14 that were part of the Microbiology's laboratory working party from 8 other European countries. They opted to include 3 different species in their simulated serum samples: Rhizomucorpocilus, Rhizopus oryzis, and Lichthemia corymbifera, formerly known as Apsidia corymbifera. And they chose different concentrations of both the DNA extraction, of the sample that will be in the DNA extraction panel A, and then as well as DNA extracts for panel B. Each participating lab was asked to provide detailed information regarding their local protocol. So this included, the volume of serum extracted, the elution volume, extraction platform, how much DNA you added, etc. And so with regards to the results, I'm going to focus on 2 separate parts. So panel A, the extraction group, they found that there was a total of 6 different automated platforms and kits that were used amongst 21 labs. And then the remaining 5 labs used manual extraction methods. And as I mentioned, Romney, there were 2 that were omitted from subsequent analysis because they did find that there was a contamination issue with Microbiology. So the rest of the data was summarized for the 24 labs only.
That's a pretty high number, though, like 2 out of 26 or whatever.
Yeah. So, it does raise the point that these are environmental, organisms and it's going to be an issue for any lab. What was interesting is the range that they found from these labs with regards to how much they input and then how much they output was quite broad. So the input volume ranged from 0.2 mils to 1 mil. Most labs did use 1 ml, and then the output volume ranged from 50 to 165 microliters, with the majority focusing on 50 microliters. They focused specifically on the sensitivity of the 24 centers with regards to the input and output volumes. And so they found that there was an increase in analytical sensitivity when you were using a larger volume. So 82.5% sensitivity for 1 ml of sample versus 62.7% sensitivity for other volumes. So quite a dramatic difference. And then with regards to the elution volume, they also found that the lower your elution volume, so 50 microliters, increased the sensitivity by about 7%, so 77.4%, versus a higher elution volume was in the low 70s. Mm-hmm. And then for panel B, the DNA amplification portion of it, similar, they found just a wide range of protocols being used. There was really a lack of standardization. There was use of commercial kits, in-house developed assays, etc. The final volume of the PCR mix that was added ranged from 10 to 50 microliters, with the majority using 20 to 25 microliters. And then the amount of actual DNA that was added to the master mix ranged from less than or equal to 2 microliters all the way to 9 microliters. So again, just, lack of standardization. Mm. And interestingly, and it really does speak to, there are certain kits that are better than others. There was a huge range in positivity from 28% all the way to 100%. So I know. So with that, they did opt to omit a a couple of the assays that had the inferior sensitivity because they didn't want it to bias, when they're trying to focus on the technical aspects of DNA amplification. They didn't want those few assays to bias that. The great thing is, especially for labs that are, using specific platforms and have no way to ever replace them, they did not find any sort of impact on PCR performance based on the PCR platform. So any platform was fine, which is nice. And then one test in particular was used quite often in the lab. So they focused on that further for further analysis. And they did find that larger DNA input volume, so greater than or equal to 7 microliters, was associated with improved sensitivity. So 95.8% compared to 81.6% when a lower volume is used. And then template percentage of greater or equal to 35. So for example, if you're using 7 microliters of DNA template and adding to 20 microliters of a final volume, that improved your sensitivity quite a bit as well, from 95.8% compared to much lower when you're using like a lower percentage. So overall, these findings demonstrate that, there are all the different parameters that you can choose for your test. The two that was the most important was the volume for DNA extraction and the volume of DNA input used for your PCR. So, when you think about it, this isn't really groundbreaking per se, but it does speak to the fact that there are these parameters can really kind of make or break your test, or at the very least improve it. But yet many labs are still offering, a variety of different parameters that may not necessarily be optimal.
Yeah. It makes perfect sense, right? More target, more detection.
Exactly.
Yet, I don't know, anyone who's gone through grad school knows you put like 2 microliters of DNA into your PCR tube and, whatever the volume, it's like so ingrained. So
Exactly.
Yeah. Well, it's
so,
also
these
really,
studies are, oh, sorry, go ahead.
It's really nice to know that the things that matter the most can be modified more easily in your lab than the instrumentation, which is often very challenging to modify.
That's true.
And so
Sorry,
ahead,
Jen,
sorry.
my sense is that, and maybe this is wrong, but my sense is that these mucorales PCRs are available much more frequently outside of the US or utilized more frequently in Europe, Asia, elsewhere, and not really as available in US labs. Would you agree? And if you agree, which sounds like you do agree, why do you think that is?
Definitely. I think there even just the commercial tests that are listed, there seems to be a lot more commercial assays available. There are different regulations, right? Especially in the US with the FDA regulations, it can make it much more difficult to have a test available. I think, that there seems to be just a lot more, and this is just an opinion, honestly, lab developed tests that's kind of happening outside of the US as well, just the capacity.
Right.
Yeah. Do you think, one thing that has always helped with standardization of these LDTs is having like a WHO standard? Is that something that's in the works possible for Micros? I keep like knocking my berries here. I have to take them off.
I know. That's a really good point because, when you think about even viral loads, like with like the WHO standards, what we use for EBV, CMV with like international units, right? So I think that it would be really promising to kind of move in that direction, even just for general not even just for mucorales, but for general PCR development. Yeah, for sure. Yeah. And then, I think just to kind of close it up, like this was perfect timing for me because as I mentioned, we're trying to develop an assay, but also we're replacing our old extraction instrument with a new version very soon. And so this is a perfect opportunity for us to, change our input and output volumes to further optimize our tests. The current protocol we're using is something I inherited when I joined, and all of our subsequent tests have been developed the same way, just to kind of maximize operation. So, with the test, with us switching and with this paper, I'm, really excited to kind of take the opportunity to see what changes we can make to our test to possibly improve it.
Yeah.
Awesome.
Cool.
Yeah, I think a mucorales PCR has been a long time coming for a lot of us in the clinical field, at least in the US. But since we're on the topic, I have to mention that a new mucorales antigen test was developed and published on recently, also in JCM. So I think maybe the needle is starting to move for this particular group of fungi. So it'll be exciting to see more testing come out for it.
It's exciting.
Yeah.
Although nothing as much fun as the cultures.
Yeah.
That is true. It's not as pretty.
They're kind of lame. They're really hard to do. Not very sensitive, but they're fun when you get them. They're so pretty.
Yes, exactly.
All right. Well, changing gears, Erin,
Yes.
what did you select?
Well, for those who know me well, this might be a surprise because I have chosen a parasitology paper, and that's not my usual area. So I, feel a little nervous dipping my feet into that pool. But I chose detection of protozoan and helminth parasites in concentrated wet mounts of stool using a deep convolutional neural network. The first author is Blaine Matheson, and senior authors Mark Couturier, both out of ARUP labs, well, at least at the time that this was being written. And it is a collaboration with TechSite, which is a diagnostic AI algorithm. And why I went out of my comfort zone for this paper is that it really struck me and what we're kind of trying to do in my lab this year as well, similar to what Jen said. So ova and parasite evaluation is very technically challenging, hard to do, and it's very time consuming for the technologist. And in the US, the positivity rate is very low. So for example, in my lab, it's below 2%. So that means for every 100 OMPs we're doing, 98% are negative. So just really, really challenging to keep up that proficiency with that low of a positivity rate. So many laboratories like mine, we were having this conversation this year, is it even worth doing OMP testing in-house? And we send it to a reference lab, or is it worth keeping it in-house? And interestingly, I'm having these conversations with reference labs. They're like, yeah, we also find it technically challenging and time consuming, but we don't have a reference lab to send it to. We are the reference lab. So definitely an issue, I think, on everyone's mind. So the idea here is, can we use digital slide scanning to build AI algorithm and apply AI algorithms to them to identify parasites, decrease the time kind of like on the microscope, scanning back and forth, looking for parasites? And can we do that while retaining high sensitivity for these parasites? And so this is a kind of companion, I would say, to a trichrome digital slide scanning AI algorithm paper by ARUP and TechSite that was from 2020. And so what they did in this very well done manuscript is they looked at concentrated wet mount for detecting helminth eggs and larvae, protozoan cysts, and they ended up, because ARUP is a reference laboratory, they have a large amount of specimens that they receive at their location, but they supplemented that further because obviously those are like US based for the most part. They had, I think I put it on here, almost all continents were represented here. I think they had specimens from Africa and Asia and Europe and Australia, as well as the United States. And they also looked at a variety of fixatives and processing methods, because again, as a reference laboratory, you can't control necessarily, only allowing for one type of processing one type.
We try, though. We try to control
Well, you do?
as much as possible. But we still get random things sent in.
I mean, we're a
Cool
system
Whip
lab and we
container.
get random preservatives sometimes, so I can't even imagine what you're dealing with.
It wouldn't be a parasitology department unless you got all sorts of weird stuff.
Yes.
Mason
Here's a
jar.
piece of tape.
100%. And they had, so the study had over 4,000 stool specimens collected, like I said, from around the globe, multiple fixative and processing methods. And what they did is they used 90% for a machine learning training set, and they held out 10% as a validation set. So a really nice representative data set that is beyond what I think most people could do internally. I mean, by that I mean everyone. So they used a 1-to-1 ratio of iodine and 10% glycerol. And the idea here of adding the glycerol is that when you're slide scanning, one issue they didn't have with the trichrome slide, but they're going to have here is that things are moving around, and that's not great for slide scanning. So the glycerol was added to kind of keep the bacteria and yeast and food particles, all that kind of stuff stationary while they were doing the slide scanner. And they also used a variety of slide scanner images from a variety of slide scanners that then they ran through the AI algorithm. And so this just makes it a stronger manuscript because it means basically the way that you're doing it could be applied to this algorithm. They measured detection of 27 different parasites, and the gold standard for detection was manual microscopy, kind of our old school, but very effective gold standard. So in the validation, they again trained the algorithm, and then this 10% validation set that they held out when they felt like the algorithm was working well. They locked it into place. This is not a continuously learning algorithm. It's set, and they ran the training set through, and it contained 265 positive specimens, 100 negatives, and their positive predictive value was over 94%. So 250 out of 265 positives were in agreement, and for negative is 94% well. So an interesting thing that they also saw with their trichrome paper is they detected 169 additional parasites compared to manual microscopy. So this is one of those things that really, I'll talk about it as we go on, but it really can get those lower level of organisms that are maybe missed or overlooked if they're very low prevalence in the specimen. So then they did discrepant analysis involving both like review of the AI software images and the microscopic review by a technologist. And when they did that, their positive percent agreement was 98.6%. And that includes both the original positives that they put in, the 265 in the training set, and also the additional 169 that they found. They confirmed that they really, were they really there? Yes, for the most part they were. Negative predictive value, depending on which of the 27 organisms you look at, was between 91 and 100. And so that shows really great performance, right? But one of the things we look at a lot is like what I'm always thinking about is, how am I going to apply this in my lab? What's this mean for my lab? Because, that's great for ARUP or Mayo or whatever, Vanderbilt, Children's, but what about my specific lab? And so one thing I really, really enjoyed, they spent a lot of time on, they took 3 technologists with different years of experience, because I really, that makes me think about, I've got my really experienced techs, but what about those have come in the last year, or those mid-range technologists that have some more experience? Like is there a lot of variation in those groups? And they found that there really was not a ton of difference between the technologists with the 3 different years of experience. In all cases, they were able to detect parasites at a lower limit of detection with the AI software compared to manual. And their manual reading was honestly like more consistent than I think we would find in my laboratory, but not studied this
definitely in mine.
But I think that some of that might be due to their super high volume. That someone with 1 year of experience in my lab means that they're doing many other areas of the lab, bacteriology mostly, or specimen processing. Whereas I don't know the setup, but if you're probably looking at consistently looking at a lot more ovum parasite specimens if you work at a reference laboratory and that's kind of your focused area. So so I thought that was really cool, and they showed it with multiple different organisms. Kind of the limit of detection was always lower with the AI software, and for the different organisms they looked at, which was really cool. So obviously, I think the strengths are the huge data set that they had, and also the validation and training set and how they structured it. I will say one of the limitations is really the only limitation we really found was that they failed to detect Chylomastix manili. I'm like, for all those parasitologists out there, I apologize. But this is a non-pathogenic organism, and it's routinely identified by trichrome. So I would say you can think about if that would be acceptable in your lab.
Let's be honest, how often are any of us identifying that ever?
I mean, that I would say in my lab, the answer is never. But
it's true.
But you must use your medical director judgment to decide.
I find it rather endearing that the authors of the paper identified that as the weakness. We couldn't get the
it really
you know, it really bugged them, right?
Yeah,
sure.
They killed them. They were so upset.
Yes, exactly.
I'm sure Mark lost some sleep.
And again, this is just on the wet count, so that it is more classically, it's more easily identified on the trichrome. So that was lovely. And kind of why I'm really excited. I was really excited about this paper. Is that, you know, I do a lot of work with laboratory automation, and that's done a lot of efficiency gains for bacteriology specimen processing. But where I find in my lab we're spending a ton of time is we call them our side labs. So parasitology, mycobacteriology, mycology, and just really they're kind of stuck in a lot of classical techniques, and the amount of time we're spending on each specimen to process it is very high, and the reimbursement is generally very low. So it's a little bit challenging because we're not making those efficiency gains in all areas of the lab. So this is one where really you can more quickly scan these slides and read them, and it's going to save time. It's going to save like eye strain of just someone sitting there looking under the microscope all day. Like at the end of the day, is the sensitivity the same as like the first slide of the day? You know, it's really hard to measure those things, but you have to think it plays ergonomics and eye strain really do play a serious role. And not only was I excited about this for ovum parasite detection, but it has so many potential applications in other areas. So gram stains, calcifluor, maybe AFB staining, you know, it's like every stain that we do theoretically could, you know, you could use a similar process, and you could have similar, you know, decrease in ergonomic issues and eye strain and less scanning, but still have that fun of when you find the parasite and you're so excited and you can show everyone, you can actually show them so much more easily. You can save these so much more easily for training. So I think there's a lot of benefit here. And just as a final note, you know, I know some labs are already using this for gram stain potentially and other areas, but we're seeing an increase in manuscripts that come in through JCM least I am. So I think that we're on the cusp of greatness with digital pathology for clinical pathology, which no one's really talking about as much as anatomic pathology.
Mhm.
But
Yeah.
I would say that
scanner, and it's going to be
that's awesome.
shared between AP and CP. So very exciting.
Perfect. Yeah,
I would say that I was going to say, for someone that's worked as a med lab scientist, working night shift, reviewing ovarian parasites and like sputums or so, I would welcome this like so badly in my lab.
Oh, yeah.
Well, Noah, I mean, I think, so I should say we are validating this in my lab. And one of the things it's made us really think about, which we did for automation, is kind of like, take this process of ovarian parasite and break it down into pieces, and who can do the different pieces. Like, can specimen processing do the processing and trichrome staining? Can they set up the wet mounts and scan them and have like a trained ASCP trained technologist come in and do the reading the next day? You can put things on different shifts. It just lends to a lot of flexibility.
Mm-hmm. Mm-hmm.
Yeah, for sure. It definitely makes the after-hour page to the medical director easier too. You can just look at the image rather than having to drive in or look at some terrible cell phone picture from somebody's microscope, which I get a lot of.
Yes.
100%.
Yeah, I think this is really exciting. I will say, though, I think it still comes with a lot of change management for the lab as well, because you'll still have those techs, I think, that maybe are less comfortable with this technology, these techniques, what does it mean for me type feeling. So it's really exciting, but still comes with a lot of training and change management with
a
it.
person, right? Like, so the AI scans the images and says, ooh,
Yep.
looks kind of like a parasite. And then you get the text.
And then the person,
Yes. So I should mention that all positives are reviewed by technologists generally. And if anyone's ever seen television instruments in clinical chemistry for CBCs, it's very reminiscent to me of that, where it highlights suspicious fields, but it does take a technologist to look at them, a super highly trained technologist to look at that and say, that's debris, that's an organism. It's definitely not a specimen in, sample out type process.
Right. And it makes it more exciting because there's actually something to look at.
Yeah.
Well, yeah. I mean, that does make parasitology a lot more exciting, even for me.
Yeah. Cool. Very nice.
Yeah, that was fun.
Romney, your half of your headgear is gone now.
Well,
so.
I was. It was heavy.
Okay.
It's making me like my neck was getting strained. So yeah, I took the whatever these are, the curly cues out.
Oh, cute.
You might see that, and actually, I feel like an O&P, like the vegetable spirals that you see. Everything comes back to
You're a microbiologist.
Yeah.
Well, what did you get for this month?
I also picked something to do with AI because, the machines are going to become our overlords soon enough. So we might as well get on board with it. So I obviously picked something to do with susceptibility testing, which I know is very on brand for me, but whatever. And so I had a hard time. I had two papers I wanted to pick, but I did focus on one, and it is entitled "Prediction of Antimicrobial Susceptibility of Pneumococci Based on Whole Genome Sequencing Data: A Direct Comparison of Two Genomic Tools to Conventional Susceptibility Test Method." So this is a paper out of Belgium. The first author is Gerardo Sanchez, and the senior author is Stephanie Desmet. And so this study took a look at different AI kind of algorithms to assess prediction from a whole genome of a bacteria, what the susceptibility might be for that organism. So we don't typically think of gram-positives as being super tricky when it comes to predicting susceptibility results, but strep pneumo can be really challenging. And so, beta-lactams are the core treatment option, and there is this increasing issue with penicillin non-susceptibility rates kind of globally. And so the challenge with detecting that or predicting it is that resistance can be very multifactorial. So usually it relates to the penicillin binding proteins of these strep pneumos. And the key ones that really seem to contribute towards resistance are PBP1A, 2B, and 2X. And so it's really hard to develop a PCR to predict penicillin non-susceptibility in pneumococcus because typically resistance is due to mutations across more than one of these penicillin binding proteins in different areas, and some mutations may confer resistance and some may not. So it actually is a little bit tricky. And the nice thing about this paper, because they were working with strep pneumo, macrolides and tetracycline, so like doxy, are other treatment options that we go to a lot. And those are a little bit easier to define. Those are actually just based on a single gene. And so they were able to look at complicated multifactorial resistance and then also kind of more straightforward resistance using whole genome sequencing. And I know in the clinical lab, we always are like, but why would you do that? It's so long to get a whole genome sequence from a bacteria, and it's going to take, a lot more time than just doing a routine susceptibility. But I think as we move towards culture-free testing. This is setting that foundation, because the thing we haven't been able to do with metagenomics or other types of technologies really well is predict the susceptibility of the bug that we've detected. So when you use AI from a whole genome sequencing to predict a microorganism susceptibility, there's really two different approaches people use. So one is kind of like, you can think of it as a lookup table. So you look for the gene that would confer resistance and then say, okay, there's a beta-lactamase here. That must mean that this bug is resistant to penicillin, as an example. And I think most of us are pretty familiar with tools like ResFinder that are available online that you can do this with. The other way to do it is to do more of a machine learning approach, which is looking at features across the genome or in selected areas of the genome, and then building a model to say which features or mutations or variations in those sequences are associated with resistance from a really big training set. So this paper, they looked at both approaches. They looked at a CDC-developed machine learning algorithm that is essentially like a lookup table in that it is looking at the penicillin binding protein profiles and not the whole core genome. And this is available free online in a program called Pathogen Watch, so anybody can use it. One of the caveats with this is it was validated using US strains. And so I know Erin mentioned in the ARUP paper, they used bugs from all around the world. And, microbiology, we have different strains of organisms that are very regional. And so there's a risk if you train your data sets using just US isolates that you wouldn't necessarily be able to recognize resistance from another part of the world because it's evolved a little bit differently. So that is sort of the caveat of that system. And then the other system that they used, which was a bit more of a machine learning whole genome approach, was the Aries cloud, which has been validated in other studies. Now, Aries, I will say, recently declared bankruptcy, the company that owned them, but they were acquired by bioMérieux. So I think we'll probably see this being used in some future form or fashion in tools. Okay, so this study, they looked at both of these different models, the CDC one and then this Aries cloud one. And they looked at 538 unique strep pneumo isolates that were recovered between 2007 and 2022 from invasive infections. They did some QC strains, like using UCAST strains as well as ATCC strains. Their reference that they used was mostly dysdiffusion. Using the UCAST method. So in Europe, they use this Mueller-Hinton fastidious for their dysdiffusion for strep pneumo. So they used that, and they interpreted it using the dysdiffusion zones using UCAST guidelines. And then when you're doing dysdiffusion for strep pneumo, one of the things that is very complicated and confusing to a lot of people is trying to test for penicillin. And so there's an oxacillin disc that is used, which is sort of a screen. And so if the zone size is smaller than 20 millimeters on this oxacillin disc, then you need to reflex and do an MIC. And so they did that for those isolates. They had MICs for penicillin for those that had that disc zone size less than 20. So the drugs they looked at, like I mentioned, is penicillin and oxacillin, right, is the predictor, amoxicillin, cefotaxime/ceftriaxone. And then they looked at 3 other kind of second-line drugs. So erythromycin, which predicts azithromycin for pneumococci, trimsulfa, and then tetracycline, which can be used often to predict doxycycline. And they had a pretty nice mix of resistance. So penicillin susceptibility in the isolate collection they tested was just shy of 80%. The only thing that was a little bit high on the susceptibility range was ceftriaxone, cefotaxime, but that you kind of expect. There's not a ton of resistance in pneumococci. So they did standard AST for all those bugs, and then they sequenced using Illumina platforms, ran the data through both the Pathogen Watch CDC program and the Aries Cloud program, and took a look and saw how well the different AI models were able to predict the susceptibilities. And so from a result perspective, actually things look pretty good. They had 32 that had incomplete or failed results. So maybe the sequencing depth wasn't good enough for them to get an accurate read using these platforms, but 32 out of 517 is not so bad. That's lower than the failure rate I think most people would see on their AST platforms for pneumococcus. And then they looked at categorical agreement with the UCAS breakpoints. So are you getting susceptible by your disk diffusion and susceptible by the AI model? And the percentages were above 90 for all of the drugs using the Aries Cloud. Using Pathogen Watch, it was above 90 for the beta-lactams, but a little bit lower for the second-line agents. And then the other thing we look at a lot is very major errors. So these are errors where your sequencing data is telling you the bug is susceptible, but your reference MIC or disk diffusion is saying, no, it's actually resistant. And the percentage, which is calculated using the number of resistant isolates as your denominator, was quite low for the beta-lactams, which is really, really good, 0%. And then quite low for trimsulfa, but erythromycin had a pretty high false susceptibility rate with both methods. So it was 14% using Aries Cloud and 53% using the Pathogen Watch. And then tetracycline, same thing, higher than you would like, very major errors. So 19% using Aries Cloud and 47% using Pathogen Watch. So I thought that was really, really interesting because theoretically, those are the drugs that are supposed to be easier to predict from genomes, right? Because resistance is just due to a single gene or 2 genes.
Yeah.
And yet they weren't able to detect these genes using their sequencing methods. So that was really, really interesting to me. And so just a couple of notes about the study. They thought maybe there's some bias in process of analyzing the next generation sequencing reads or the assembly that was leading to these lack of detections for these genes. So depending on where the gene is placed, that might cause some confusion. And then the other thing is you needed to have a pretty good percent coverage of these genes for the system to say, yeah, there's a TET-M gene, which would confer tetracycline resistance. The platforms required 90% coverage of that gene. And often when they were calling something susceptible, when it was actually resistant, it was just shy of that 90%. So again, it kind of speaks to the stuff that Jen was talking about, how optimizing your molecular testing methods so that you have really good sensitivity for these things is good. And then the other thing that they noted, and I thought this was right up my alley, I love this, but for trimethoprim sulfamethoxazole, they did have lower than desired categorical agreement. So it was 85% using Pathogen Watch and 81 using the Aries platform. And what's interesting about that is both those systems are trained using CLSI breakpoints, but they analyzed it using UCAST breakpoints, and those breakpoints aren't the same. And so again, it just goes to the point of you need to be thoughtful of what is your source of truth in your training data. And often the training data is just susceptible, intermediate, or resistant. There's not always MIC level data in there, which can make it really tricky. So
that's very interesting.
yeah, right. I thought that was cool. So it does kind of highlight, the issues of just looking at the categories and not actually predicting the MICs. And you could predict, as breakpoints change, because they always do. If you've developed an entire AI model using SINR, and then the breakpoint changes, like the entire model is completely useless now. So anyways, so I thought this was a fun paper. I do think this is kind of the future of susceptibility testing. As much as it pains me, I do love my phenotypes. One day we will get rid of the authors did a great job of this. I do want to give one honorable mention, which was for a paper looking just at PCR based, which is kind of that lookup table. Is if there's a gene, then is resistant. And this was a paper that Lars Westblade's group put together, looking at gram-negative antimicrobial resistance genes from positive blood cultures using a BioFire panel. And so their BioFire bioMérieux has a new panel that looks at like a very extensive list of resistance genes. And so they evaluated that to see, well, if you had a whole bunch more genes you're looking for, does that actually do a better job at predicting resistance and susceptibility? So I won't get into that one, but people should read it because it's also very interesting. Probably a little closer to prime time for us than the whole genome sequence.
The whole genome. Yeah. Very cool. Very cool. Nice. Well, I guess we can wrap it up with a non-digital, non-AI, non-AST paper.
You're not going to do an AST paper, Ellie. I really thought.
Someday, before I retire, maybe.
Oh, my goodness. And I'll just be so shocked.
Oh my gosh, yes, everyone's just going to fall off their seat, I'm sure. So for my choice, I selected a manuscript by Andrew Levin and colleagues entitled A Novel Single-Tier Serologic Test to Diagnose All Stages of Lyme Disease, which was published in August of this year. And the reason I chose it is really because of its ingenuity. So like you all know, the algorithms that we currently use for Lyme disease testing require 2 or 3 tests to be performed. That takes time and resources. And then they're also really limited in sensitivity during that first 1 to 2 weeks after infection and so on. So wouldn't it be nice to maybe have a single test that outperforms all of our current methods combined? And so that's what this group really kind of looked to develop. So what they did was essentially create a single tier Lyme serologic test that's based on detection of multivalent antibodies. And I'll talk about what that is. But these antibodies simultaneously bind to different epitopes of the Borrelia burgdorferi VLSC protein. So VLSC stands for VIMP-like sequence expressed protein. It's a surface protein that has both variable and invariable regions. And one of those invariable regions is known as the C6 peptide. So what this group noted was that epitopes that cause false positive results on C6 only or VLSC only based ELISAs are not shared. So what that means is that a false positive result on a C6 ELISA or assay is not observed when that same sample is tested by a VLSC-based ELISA and vice versa. So with that observation, they designed an assay to detect individual multivalent antibodies that recognize both epitopes in the C6 peptide as well as in VLSC as a way to enhance specificity. And it's maybe hard to envision, so I'd encourage anyone interested to take a look at the image in the paper. but the ELISA is designed such that the VLSC antigen is adhered to the solid phase of your ELISA plate, whereas the C6 peptide is conjugated to streptavidin HRP, and that's what's used as the enzymatic reporter molecule. So the only antibodies that would be captured in this ELISA are those that can bind to both VLSC and the C6 epitope. And so the ability to detect both of these antigens simultaneously ultimately leads to higher binding stringency and theoretically lower false reactivity as compared to assays using just a traditional secondary enzyme labeled antibody. So collectively then, this allows for a lower cutoff threshold to be established compared to conventional ELISAs, and ultimately an increased ability to detect lower levels of specific antibodies that are present in early disease. And that's actually exactly what they showed. So with their hybrid ELISA, they basically showed that they're able to detect a higher proportion, about 96% of patients with acute Lyme disease, which is defined as patients with an erythema migrans lesion. And that's compared to 76% positivity of the modified algorithm when performed in that same sample set. They showed that sensitivity of their hybrid ELISA was similar to the modified algorithm in later stages of Lyme disease at about 100%, and then specificity for their hybrid ELISA was 100% compared to about 95 to 98% for the current algorithms. So it's it's a preliminary paper or a preliminary assay study, but it was really exciting because it's, I'd say, one of the first that was really significantly able to improve sensitivity in acute Lyme disease cases using an ELISA modality that a lot of labs are able to implement quickly. So it'll be interesting to see where that goes in the future. But I have a love-hate relationship with Lyme, so I'd love a single-tiered approach.
Don't we all?
No. Yes. But yeah, mine was kind of simple. Well, the assay is not simple, but it's a short and sweet paper.
That's cool.
So yeah.
I was going to make a joke about no more Western blots, but I've been schooled by Lily. We got rid of those a while ago.
Oh, yes, good. Some people are hanging on to those, man, like a life raft. Cannot let go of the blots.
I didn't know that. I'm super dumb when it comes to serology now, so I did not know that either.
Oh, you are not. You are not. Yeah. Well, this was fun. I think we covered a lot of ground.
Yeah.
Yeah.
So, is anyone making the Rebecca Lansfield eggnog for Christmas?
No.
No.
You share.
Do you not know about this?
No.
Oh, so she would make this eggnog every Christmas, and the I think it was like kind of before we had, I don't know if you pasteurize eggs, but you keep them in the fridge and so you don't have as much salmonella contamination on them. And so the idea was that there was so much booze in her eggnog that even if there was salmonella in it, it killed off the salmonella and you could drink it no matter what. And it like fermented for like a while. And there's like this great video where they actually added salmonella to her recipe. And then plated it out. No, but nobody drank it, sad to say. Nobody trusted it that much. But it does indeed. So the moral of the story is lots of booze over Christmas is the way to help.
It's much safer. Yeah.
Keeps the bugs away.
Keeps the bugs away. Yeah.
I think I can subscribe to that.
Yeah. I'll see if I can find the recipe. We'll include it in the show notes for
the show notes.
to partake in. Yeah. It's a good time.
Well, thanks, Romney. And on that note, thank you, Jen and Erin, for joining us today. It was great to have you on.
For having us.
Thanks for having us.
And we hope everybody has a great holiday season. And we will see you again in January.
Sounds good. Thanks, everyone.
Thank you.
Bye. Happy holidays.
Happy holidays.